Thank you very much. So this research topic is one that's very important to me personally. I have suffered from hearing loss for my whole life, and for several years I've been a hearing aid user. And like most hearing aid users, I am really dissatisfied with how well hearing aids work, particularly in noisy environments. So that's the subject of my research, and that's what I'll be talking to you about today. Actually, I'll be speaking more generally about augmented listening technology rather than specifically hearing aids, since in the last 2 or 3 years, the market has shifted quite a bit. There have been some new technological advances as well as regulatory changes, and as a result, hearing aids are becoming more like headphones, headphones are becoming more like hearing aids, and there are a lot of new exciting applications for researchers to explore. So in addition to just developing algorithms to help people with hearing loss to hear better, we can work on augmented reality technologies like translating speech from one language to another in real time. This device is used for soldiers to let them talk to each other during gunfire that would otherwise temporarily deafen them. You can even imagine very impactful applications like making all of your friends sound like a squirrel when you're walking around. So really the possibilities are endless. But there is a big roadblock to progress in augmented listening, and that is noise. So noisy environments like restaurants, bars, clubs. Actually, one of the worst is poster sessions at conferences. I've found listening devices will just stop working. Either they will amplify everything, including noise that you don't want to hear, or in the case of mine, they will get confused and cause very annoying distortion. So the problem is noise. The obvious solution would seem to be let's try to reduce the noise. And there are a number of strategies that listening devices use. So a simple hearing aid like this one, or the ones that I wear, use adaptive filtering, which I'm sure everyone here is familiar with. Learn the statistics of the noise, and then filter it out. Most of the attention and definitely most of the money these days is going to machine learning methods of noise reduction. And machine learning is very good at telling apart different types of sounds, so it can distinguish between speech and music, for example. But it doesn't work especially reliably in complex listening situations where there might be different types of noise or you don't know what to expect. So this is one product that was hyped quite a bit, the Hear One by Doppler Labs, which uses machine learning to try to enhance listening and reduce noise. Unfortunately, it didn't work very well at all, and they're no longer in business. But I applaud them for trying. One that does work much better is this one. This is the Hearphones by Bose, and this uses beamforming to do directional noise reduction. So it has a set of microphones, and it can steer a beam in front of you so that sounds in front are amplified and sounds to the side and behind you are attenuated. And I love that product. It works very well in a restaurant or a bar, so you only hear what's in front of you. The problem with that kind of noise reduction, though, is it doesn't sound very natural. Humans are used to hearing everything around them, and just hearing in one direction is sort of like talking into a directional microphone. They took that one away. Yes, that one. The proximity effect, that's okay. But it causes distortion. So what I propose instead is that we don't think of the augmented listening and noise problem as a noise reduction problem. Rather, we should think of it as a remixing problem. So I like to think of it as a mixing engineer sitting in my hearing aid with this big mixing console and doing different processing to different sources. Sort of like when they're making a movie soundtrack, they have separate tracks and recordings for the dialogue, the music, the sound effects. They're going to process them differently and then combine them in such a way that you can understand the speech, emotionally react to the music, and enjoy the sound effects as well. So it would be wonderful if our listening devices could do the same thing. Unfortunately, they do not have access to those separate recordings that they can easily mix together. So that's the signal processing challenge. We have to, from the mixture of these sources, recover them so that we can process them. So I like to think of that as a multi-user communication problem. The solution is microphone arrays, just like beamforming, but it's now a MIMO channel, not just a beamformer. This is my assistant, Mike A. Ray, who's wearing a large microphone array, represented here with these stickers. So if you have a large number of microphones, you can use those to separate these sources and filter them. So suppose we have N sources, which could be speech, music, noise. They don't necessarily have to be point sources. And we have M microphones, hopefully more microphones than sources. Then we have this MIMO channel, which in the frequency domain is an M by M matrix. Each entry in the matrix is a transfer function that depends on the path of reflections that the sound takes to propagate from each source to each microphone. So for the purposes of this talk, let's assume that we have measured this channel or estimated it, which is not easy to do, but can be done. The question I want to answer is how do we then take those microphone measurements and generate the signals at the left and right ear so that we have this new mixture of sources that sounds better and is easier to listen to. So it's actually a very interesting problem. There are constraints involved that don't show up in other multi-channel audio problems, such as speech recognition or voice conferencing. So each of these bullets is actually a whole conference paper, but I will go through them fairly quickly. So on the left of these equations, one for the left ear, one for the right ear, is the output of our filter. We're trying to design these filter weights. And on the right side is what we would like the output to be. So this diagonal matrix contains real valued gains, which vary with both time and frequency. Frequency, of course, because we might want to boost some frequencies relative to others. They vary with time so that we can control the dynamic range of the signal. That's one of the most important things that hearing aids do and that other augmented listening devices can do to ensure that sounds are audible but still comfortable. So if my hearing aids boosted everything by 30 decibels and someone slammed a door very hard, it would be quite painful. And because it's nonlinear, compression is one of the reasons that hearing aids, I think, perform so poorly in noise. So I'm excited about doing compression on different sources at once. So this term represents spatial transfer functions from each source to the left ear and the right ear. So that captures things like the head shadow effect, time difference between the ears, the shape of the outer ear, which is how humans can tell what direction a sound is coming from. So if you have a conventional beamformer, like a delay in some beamformer, it will actually sound like everything's coming from the same direction, which is presumably not what you want, and could be quite dangerous for a human listener. So we need these extra constraints to make sure that we preserve spatial awareness. This term is for delay. This is a real-time system, of course. The sound is coming in, and I'm listening to it. I want to hear it as if there's nothing there. So the delay needs to be less than roughly 10 milliseconds to be imperceptible. That's the general rule of thumb. And that is a challenge that hasn't really been investigated very much yet, but one that we're starting to look at. And then a final point. Since we have all these extra constraints, We really need as many degrees of freedom as we can get. And fortunately, speech signals, many types of music, and other natural sounds are sparse. So in this time frequency representation, it's safe to assume that only one or two entries of this vector will have significant energy. And that makes this filter design problem a lot easier. All right, so that's enough math. Let's hear some demos. So this is a recording I made in my living room using this array, which is very similar to the one in the Amazon Echo. It has 7 digital MEMS microphones all around the circumference and in the center. And what you're going to hear is myself talking, and then 3 British people reading the newspaper. And in the first recording, you won't be able to understand what I say. And in the second one, you will still hear the others talking, but should be able to understand me. So I'll play the first recording. Really? Did we turn the speakers off after all that? Yes. Oh, it's muted. There we go.
No, 0.
We came in early just to be Whoops.
Many beautiful colors.
All right, so now I'm applying this filter that's designed to add 20 decibels to my voice, take away 20 decibels from the other 3 voices, and also compress them by different amounts. So you should be able to make out what I'm saying in this one, even though it doesn't sound especially nice.
Happy birthday, Mom.
I'm wishing my mother a happy birthday. And it is my mother's birthday today, so happy birthday, Mom. So obviously that wasn't as clean sounding as it could be. If we want to do better, we need more microphones. So unfortunately, most hearing aids only have 2 or 3 microphones. Maybe they can share data binaurally, but that's not quite enough. So our group has recruited a team of undergraduates who are working on building various prototypes. They have all of our microphones now and are building with them, so that's why I have these paper microphone stickers. But the idea is to build arrays that can be worn on the waist, the chest, the hat. The more space they can cover, the better. And with enough spatial diversity, we should be able to do much more aggressive filtering and do new types of audio processing that current devices can't do and current engineers at these companies aren't even thinking of. So to do that, we need to figure out how do we design these things, what are the trade-offs, how do they scale, how many of these microphones do we need, and those are all open research questions. But once we answer them, hopefully in a few months we'll have some working demos, we'll have some data sets that we plan to make public, and then we can show off these new applications that will let us remix sources as if we had that mixing board in your head, apply different processing to every sound in real time in a way that is transparent to the user and sounds like you're not even wearing it. So that is our vision. Thank you.
Are there any questions? Okay, so I'll ask a question. So how many microphones have you put on mic array so far?
So right now we have a helmet, which I don't have here because it is being worked on actively. I think that has maybe a dozen or so right now. I don't know how to use FPGAs, so I hired undergraduates, and they're struggling. So that's sort of the bottleneck at the moment. Maybe you can help. But yeah, we want to sample all these microphones. The record for a helmet-mounted microphone array right now is 32 from MIT, so we want to put at least 33 on it. Yes?
Thank you. So I understand you need spatial filter. What do you mean by time varying filter? Why you need time varying filter?
So there are a few reasons it's time varying. The first is to perform compression. So compression is a nonlinear operation because it's essentially automatic gain control, and that is implemented as a time-varying gain. The other reason is to take advantage of sparsity. So a one-time frequency instant is maybe a frame of about 30 milliseconds. And within that frame, maybe only one or two of these sources is active, so we only need to apply constraints to that source. But in the next frame, it might be a different source. So that's why the filters need to change over time. And that is something that's fairly commonly done in audio, especially in single-channel source separation, which relies on more machine learning techniques. But that's a very high delay algorithm, so that's the trade-off.
Any other questions? Okay, so let's thank the speaker again.
Thank you.